Okay, so so since the recordings are, I'll talk about more serious stuff. So the the so now we see the delta x, which is the invariant on this variety, and by definition, actually this is not the original definition. This equivalence is something called the Fujita-Lee criterion, and that we say the delta x is at least one if and only if x is k semi-stable. So basically we have an invariance to measure how how stable the final variety is. And the first term, which is about the stack, is if I fix any positive number between 0 and 1, and now I look at all final varieties whose delta is at least this number, delta 0, then this will give me a finite type open stack, substack. So of course, the stack of final variety with fixed volume and fixed dimension is not finite type. I mean, we know many examples. So you have to specify a little bit other conditions. And here the conditions we specify is the delta invariant has a lower bound. So particularly if we look at if I take delta 0 to be 1, then that just gives me the open stack of k semi-stable, open substack of k semi-stable final variety, which is finite type. But actually, the function that if I take delta x, or I have to modify like take a minimum of delta x under 1, then this function is actually constructible and lower semi-continuous. So somehow I really stratify my stack of all final varieties. Then there's this like a big open set, which is a semi-stable one. Then all other like a not unstable part, they still form like a strata. So that's, I mean, if you look at the vector bundle case, you can do the similar story by stratify the vector bundle with fixed determinant or fixed rank by some some function comes from the Hadamard filtration. So each strata is locally closed, and if you take the union of the strata for larger than delta 0, for any 0, then it's open. So basically, Chenyang proved the finite type part, and Bloom, Yuchen Liu, and myself proved that it's an open subset. It's the openness part. So now we have the stack. I want to say that I want to discuss the good modular space. I mean, that's actually the more delicate part. So basically, good modular space, you can, I mean, I think this notion was first introduced by Jalo Alper. But for us, we just think about it as locally, entire locally around each close point on X. So there is a morphism from the stack X to some space X. Here X is only algebraic space, such that entire locally around each X, if I take the base change of F, then it just comes from a reductive group G acts on a affine scheme, and the entire neighborhood is given by the invariant function of this action. So particularly G here, you can just take it to be the inertial group, or in our case, just the automorphism of the final variety corresponding to this point. So somehow you can just think about the good modular space is is some morphism attached to your stack, such as entire locally, this morphism is just given by this morphism of spec A mod G to the invariant function. So this kind of standard GIT morphism. I mean, of course, this is very, if your stack has such a morphism, it's a very nice structure. And our theorem say that X, my stack of K semi-stable one, does admit a good modular space, which is separated. So this is, I think, very special for K semi-stable. I mean, it's very hard to write down something like a stack which has a separated good modular space, but the K semi-stable one does have one. And to check this, we actually use some general criterion by Harper-Leisler and Henlos. Oh, the original theorem was proved by together with Harper, Bloom, Harper-Leisler, and myself. But we use this general criterion, which says that a finite type stack, which is a fine diagonal, which is certainly our case, has a separated good modular space if and only if it satisfies two valuative criteria, which I'll specify the more subtle one in the next page. But this two is called the S completeness and the theta reductivity. I think in recent Jaro's talk, he started to call it like something like S reductivity and the theta reductivity. So I think they haven't completely agreed with the terminology yet. But in the original paper they wrote, it's called the S completeness and the theta reductivity. So, but if you say something like called the S reductivity, you don't be too confused. Maybe I think it probably just means the same thing as the S completeness. So let me describe you what S completeness is. So now I start with adding DVR and with a uniformizer pi. So I look at the stack, the RST with locus pi is equal to ST, module the action by GN, such that the weight on S is 1, on T is -1. So it's an R action. And now if I take the quotient, I mean, basically you can easily say the quotient has, I mean, this SR has 4 strata. So the deepest strata is 0. So it's a gerb, it's 0 more GM. Then there are 2 like one-dimensional strata. One is S equal to 0 more GM. And another one is T equal to 0 more GM. And then, so these are like 2 equivalent lines. And then there is a surface-like object, 2-dimensional object SR. So now you can easily say that if I take the open set S is not equal to 0, then the SR is isomorphic to just 2 spec R. So particularly if I take the union of 2 open set S is not equal to 0, T is not equal to 0. So in other words, I just look at the complement of 0 in SR. Then I just got 2 spec R. And they share this like the largest strata, which is given by spec K. So in other words, I just glue 2 spec R along the spec K. So in other words, I just got a double pointed line. And S is called S complete. I mean, a stack is called S complete if that this double pointed line mapped to the stack can be uniquely extended to a morphism from this surface type object mapped to this line. So somehow you can uniquely fill in this puncture surface to the entire surface. So okay, sorry. Here then, if you apply to our theory, let's just say if I have a family of K semi-stable Fano variety over this object SR, take out 0. So which just means if I use this isomorphic, that just means I have a 2 family of Fano varieties, which are isomorphic along the genetic fiber, and they're all K semi-stable. Then this just say that I can extend this morphism from SR mapped to 0 to SR mapped to X. So particularly, I got the consequence that the 2 special fiber on the 2 family, they actually have a common GM equivalent degeneration, which is still K semi-stable. So somehow you have that's what you prove. I mean, to fill in this kind of, I mean, this S completeness criterion is just equivalent to find this GM filling in of K semi-stable Fano varieties for this family of Fano variety over this puncture surface. So that's what we proved. And we proved a similar criterion called the theta reductivity, which is in some sense, I think simpler than this one. So that's all I want to say about the exist part of the separated good modular. So any question? Okay, so if there's no question, let me move to the properties. So the next thing is the good modular space we got in the previous step is actually proper. So if you think about how KSPA theory to prove proper, so basically it follows from the minimal program. Here somehow we don't. So far we don't have a direct construction of the feeling. So if you want to show proper, you basically just have to show that if I have a family of Fano varieties over punctured disk K semi-stable, then I can fill in the fiber over the central point, such as still K semi-stable. So if you apply the theorem I mentioned at the beginning of my talk by Chili and myself more than 10 years ago, we can always fill in the fiber with some Fano varieties, but it might not be K semi-stable. So in other words, it might happen that the delta of the central fiber is smaller than the delta of the generic fiber or one. So then somehow you want to increase to replace the central fiber to increase the stability. In other words, I want to find another family such as over the puncture disk, it's still my original family. But now the central fiber, so this new family, I call it X prime. So then I want to that the delta of this X prime K kappa, the new central fiber, the delta is larger. And because we already proved delta has find many choices, each time you increase it, you will stabilize at the point that the delta of the central fiber is the same as the delta of the generic fiber or one. So that's a plan. So, however, at the end of the day, turns out it's not actually directly construct this X prime. So yeah, again, we actually construct this over the entire SR in this surface, such that this spec R corresponds to S not equal to 0. And the new fill-in corresponds to the T is not equal to 0. That's a new fill-in. So, however, there is this like the deepest strata. So we want that the deepest strata have the same delta as your delta you start with, because delta is only going down. So if you're along this line, the original central fiber X kappa degenerates to this deepest strata, then the delta only can go down. But we want to not go down. We want to be the same. And then we want to pick up this new feeling carefully, such that along this like a new direction, this direction T is negative direction, the delta indeed increase. So somehow the upshot here, I want to say that it's not just to replace one by another one. We actually fill in the entire surface family. And there is actually one more object, which is just the central guy sits in the over the deepest strata. But as I said, unfortunately, we don't have a direct construction of this. So we can do this using some abstract theory, which is called a theta stratification by HyperKahler. So any question so far? So basically, the theta stratification, as the name suggests, it's kind of a stratification. I mean, we already have a stratification. And to satisfy the theta stratification, one condition you need is for any unstable object, there exists a GM degeneration of X0, such that the delta X is actually the same as the central fiber, as the GM degeneration, allow the test configuration. And this GM, this delta of the central fiber is actually computed by the GM action, by the valuation induced by the GM action. So and this exists. This existing part was actually quite challenging, and that was proved by, I mean, it's something we call the optimal destabilization, and that was proved by Yuchen Liu and Zhiyu and myself. But there is slightly, this is still not completely enough, because to apply hyperlysis theory, we actually need that this such kind of optimal degeneration is unique. If you just use delta to be the environment to test your stability, then often it's not unique. You might have a more than one divider such that the delta is all get to the same minimal number. So, however, there's a trick to get around this that was done by Bloom, hyperlyzer, Yuchen, Liu, and myself. So basically, we can refine this delta to be a R2 valid function. So here, R2 has alphabetical order. So such that the first one is this delta X, but it's alphabetical order. So now I can look at the order degeneration which attain the minimal delta X. And then among them, I pick up the second minimum. And I'm not going to specify what the second minimum is. But if you put all this together, that will give you a uniqueness of this optimal dispersion. And the existence is essentially just from the same without here. So if you put this together, we show that this stack of Fano varieties admits something called a theta stratification, which is not exactly not this one. It's actually some refinement of this one, but the open set is still just the K semi-stable one. So, but one mysterious questions I always have is, there are some other no stratifications of Fano varieties using different functions, which very much similar to theta stratification, but all of them comes from certain kind of K-stability theory. And while these stratifications are different, they always have the same open part, which is the K semi-stable one. So somehow that just makes me wonder, this K semi-stability must be some very canonical object. This if I study the stack of Fano variety. So, but however, I don't have a way to describe what the canonicity here means. So I leave it as a question. Do there exist other theta stratification of Fano generally, such that the open parts are different with the K semi-stable one? I mean, I would say I 99% believe the answer is no, but I don't have a proof, and there is still 1% chance that actually there may be some other theory. Because if you think about the GIT, if you change the linearization, then not just a stratification change. Of course, the semi-stable open locus often are different with each other, but somehow this like intrinsic theory for Fano varieties, even there might be different stratification structure, but somehow the open part always yields the same one. So I find that quite mysterious and quite spectacular. So one thing I said in the last page was this like the existence of optimal dispersion. So that a major technique part to prove that is something we call the higher rankifier generation. So I want to use this this page to discuss a little bit. So now if I start with a Fano variety, I mean, actually this condition not necessarily, but just give you some picture. So if I have some DLT Fano model YE, so Y map to X is birational, and YE is DLT, and minus KY minus E example. That's what I call DLT Fano model. And now I take, here, this E should be D. So now I take the coefficient one part of this E, I call it D. So now I look at then of course YD, they are simple normal crossing another genetic point. And then this dual complex looks like a simplex. So the theorem say if I have a different V and W, so inside this simplex, the induced gradient ring are actually isomorphic with each other. So in other words, I mean, the V and W just differs by some grading, but the gradient ring, as abstract gradient ring, they are just completely isomorphic. So particularly this concluded that it's finite generated, and with a little bit more work, you can say that the approach of them is KLT. So particularly this, in other words, no matter V and W, what V and W you choose, as long as it's in the interior of this dual complex, then you got the same degeneration. The degeneration will be to the same Fano KLT Fano variety. So we call such valuations W to be special. So special just means it's finite generated and the approach is KLT. So actually, I find this question very interesting that if I have a complement, so which is, in other words, is just some effective divider d equal to minus k. Sorry, I forget to write the one condition that xd is low canonic. That's what I call complement. Xd is low canonic. So then I can just look at all the LC planes, which I write drxd. That's the dual complex of xd. So I want to ask how the spectral valuation distribute. So particularly, I mean, we raised a bunch of questions about that. So one question, I mean, a weak version of question is that if I assume that every guy in my dual complex is special, actually, can I find a finite rational chamber decomposition of this dual complex such that the V and the W, the gradient ring, are the same as long as they belong to the same chamber? So somehow there is kind of like cone theorem type structure. There's like a geology structure, but now it's not for combination of divider. It's for valuation, and so it has to. I mean, you might wonder if why I need a KLT condition. How about I just pick just the finite generation condition? But it seems that doesn't work very well. So somehow you really have to have a KLT and so finite generated and the KLT together, and then there's a chance all those valuations might behave much better than you only consider the finite generated one. So this is somewhat a technical question, but I find it quite interesting. But it's very unclear to us for now. So any question? So my last page about general case stability is that I want to mention some examples. I mean, I think Vanya will give a lecture on more about the examples. So let me just mention that currently there are, I mean, two types of examples people are very interested in. One are threefold because we have this Mori-Iskowski classification, and also, well, of course, interesting hypersurfaces. And another research direction by Asher, DeFleming, Liu, and Zhou, and others is that we can consider that we vary the coefficient T of a pair and study the wall crossing structure of the different moduli. This actually will play some role in my application I will talk about in the second part. But there is a general theory for Fano varieties doing moduli like this. But for instance, there are two, I think, very interesting questions about the existing Fano moduli. So for Fano threefolds, I think there's a chance that all smooth Picard number one guys are K semi-stable. I think this is now up to the degree something like 16, right? I think for 18 and 22, the last two we don't know this. And then of course for hypersurface, we want to ask whether every smooth guy with degree at least 3 is K stable. And Abel and John has so far the strongest statement along this direction. And also for cubic, Yuchen has Yuchen proof for fourfold, but in general, it's still wide open. So I think I'll leave this more discussion of examples to Vanya. I'll talk about a very simple example in my application. So now I want to switch to the second part of my lecture about, I mean, some like new work done for HyperKahler variety. So I mean, this is a module of varieties. We want to say some collaboration, and I think this is some potential zone that some collaboration can happen. So I think 7 years ago, maybe Lada, Shaka, and Vasan has this very nice result that if I consider a general cubic fourfold X, so I fix this, I consider all smooth cubic threefold YT. And then you can study the relative Jacobian fibration. And this was known as to be a Lagrangian fibration. And what LSV, Lada Shaka Vasang, LSV proved that actually we can have a explicit compactification of this Lagrangian fibration to be a projective Lagrangian fibration over P5. And this construction is explicit. Actually, if you think about this, so you have to study the degeneration of Fano threefolds, and you might want to study the degeneration of intermediate Jacobi of the Fano threefolds. But for higher dimensional variety, the degeneration of intermediate Jacobi seems to be quite difficult. So what they observed is that this degeneration process can be, is basically exactly the same as the degeneration of some prime variety together with some degeneration of curves, if you find the curve and the prime variety correctly. So in other words, you can reinterpret this degeneration of intermediate Jacobian as degeneration of prime varieties. And because we know much about degeneration of curves, then we can say a lot more about the degeneration of prime variety. So the major consequence they got from this explicit construction, one of the main consequences they got from this abstraction that actually the compactification is smooth. So, of course, it would be very nice if it's a new deformation type, but they also prove that it's deformation equivalent to the OG10. So one of the two sporadic families found by Kiran O'Grady more than 20 years ago. So we want to do a similar story, but in our story, we actually don't have any way to control the degeneration of the intermediate Jacobi. So at least we don't have any control over codimension 2 point. So we basically let minimal program take care of the degeneration over codimension 2 point. So our theorem, basically proved by Saka and Yuchen, Liu, Zhiyu, Liu, and myself, is that if I have a projective normal variety, and I have some quasi-projective map from something I call J0 map to B, and I assume that J0 is a Lagrangian fibration of F0 J0, and J is quasi-projective, so the image might not be the entire B, but I assume the codimension of the complement of the image is at least 2. And then I further assume that a general fiber is a simple abelian variety of this morphism. Then we prove that there exists a irreducible terminal Q factorial symplectic variety, which gives the Lagrangian fibration over B. But so this J bar is a irreducible symplectic variety, but it might not be smooth. The trade-off, we use MMP, so the trade-off is the best thing we can get is terminal or Q factorial. So basically, Saka proved this without condition 2 that you can always compactify it as a symplectic variety. But then if we know a general fiber is simple abelian variety, then it's actually irreducible symplectic. So the ingredient of this proof has 2 parts. So to get the symplectic variety, in Saka's work, you need a minimum program. And then to prove the irreducibility, you actually need the decomposition theorem of singular Calabi-Yau varieties, which was proved by a bunch of people, combined bunch of people together. I think the last part was probably done by Horin Piternel and Guancica, Henry Guancica. Right? So, but it's combined by some former previous works done by also by Kebikas and Stefan Zhu as well. So anyway, to prove this kind of compactification, we need 2 recipes. One is a minimum program and one is decomposition. But these are just 2 general theorems. And as a result, we just get some irreducible symplectic variety, but may not be smooth terminal Q factorial. So we want to apply this to one example. This example, the open part was already studied before by, for instance, Iliev, Manuel, and Markushevich. So it's somehow dual to the example in LSV. So now I still fix the general cubic fourfold, but instead of consider all the threefold containing it, now I consider all fivefolds containing it. So then if I consider only the smooth ones, I still got a relative Jacobian fibration, which now is of dimension 42. I mean, of course, in the original LSV case, the dimension is 10. So then the theorem I proved together with Yuchen Liu and Zhiyu. So by the way, Zhiyu Liu is actually a first-year graduate student working with Yongbin Ran. So I mean, I think everybody know who Yuchen Liu is. So basically, this Iliev, Manuel, Markushevich Jacobi fibration, it actually admits a compactification, which is a irreducible symplectic variety. I mean, terminal Q factorial, and the base now is not a projective space; it's only a weighted projective space. So particularly, I would say this probably suggests that this compactification is not smooth if you believe that the adding Lagrangian fibration of a smooth HyperKahler manifold, the base is Pn. I mean, but I don't know how much people believe that, but yeah. And also we know that the second Belli number of this J bar is at least 24. So particularly, I think this is a completely new examples in HyperKahler varieties. Unfortunately, we don't know it's smooth, and my guess is it's not. But yeah. So from, I mean, of course, we want to apply the previous proposition. Then what do we have to do? So we have to compactify BSM. So this open part only parametrize smooth guy, but now I want to compactify this. And then I want to show that the Jacobian vibration structure can be extended over codimension 1 point. So here, somehow, I think the difference between our strategy with the LSV is the LSV, they got the compactification of the base, and also they got the explicit compactification of the total space. Here, I mean, we cannot get the compactification of the total space. We don't have a, sorry, no, we can. We don't have an explicit compactification of the total space. We only have a explicit compactification of the base, and we know something in codimension 1, and then the minimum program take care of the rest. So somehow we, instead of compactify the entire Lagrangian fibration, our main work is on compactify of the base. And one can easily show that if this kind of, if I have like a open Lagrangian fibration, if it can be compatible as a projective HyperKahler variety, then the base can be choose uniquely. So in other words, if you want to compactify the base, there is to get a HyperKahler compactification, then there is only one way to compactify the base. So somehow you have to choose this one compactification carefully. But of course, it should be the somewhat canonical one from the geometry. So that's what we want to study here. So remember, the open part of our base is basically the moduli of Fano cubic fivefolds containing a fixed cubic fourfolds. So if I want to compactify this, then of course I want to compactify the moduli of cubic fivefold. So this is what we consider the modular problem. So I consider modular problem of cubic fivefolds, and then a hyperplane, because we want to get this fourfold. Then this, I mean, we actually don't need the case stability here, although somehow I believe this should be the same as K-moduli, but we just use GIT. So So when you use GIT, then there's a choice of ample line bundle. So the choice basically is depends on the ratio of B over A. So A is a pullback from the first object, B is a pullback from second. And actually, this kind of thing was already started by for instance, people like Gallardo, Martinez Garcia. So they show that, particularly they show in this case, the way GIT problem happens between 0 and 1/2. So uh, here I don't need this epsilon. Epsilon is for below. So basically, if I look at the 1/2 point, then the semi-poly the stability of y and h is precisely equivalent to the stability of the intersection, the stability of fourfold. So this is the 1/2 part. So somehow to study this 1/2 guy, it's exactly the same as study the base. But what we are interested in the stability condition when it's half minus epsilon, when epsilon is between like very small. And by general GIT theory, we know that there is a open stack containing the M1/2 minus epsilon as a stack is contained in M1/2. And as a space, there is a projective movism from the GIT moduli space to GIT moduli of M/2, and which by Gallardo Martinez Garcia series is M4. So this M/2 actually will crash lots of K semi-stable one into one. Basically, just crash them into one point, which is just the intersection of the fivefold together with the hyperplane. So I believe in the LSV, if you put there, if you just forget the total space, if you just study the base, then that's actually is essentially, if you study the fourfold, the threefold containing it, then that just basically study the epsilon GIT stability of this. And we know in that case, it's going to be a P5 bundle over M4. So that's why the Lagrangian base is a P5, because that's just a fiber of this map to PM4. So somehow we see this kind of two construction, like dual construction from the two end of this GIT variation problem. So now we want to compute this, and we can basically compute out that if I over a stable point X, which is a cubic fourfold, and we even assume there is no automorphism. I mean, this is not so important, but we can assume that. So this cubic fourfold, general cubic fourfold without any automorphism, then for this point, the fiber of this morphism, the fiber of this morphism is weighted projective stack of this guy, and the fiber over phi of the underlying space one is just the corresponding weighted projective space. So in other words, the fiber, I mean as a phi moduli space is just the projective moduli stack, and as a cos moduli space is just a weighted projective space. And to calculate this, we actually really need that the epsilon to be very small. So we need the help from the M/2 from the information on half. I mean, let me just quickly mention the calculation. So let's assume x is just given by this equation, and h is x0 equal to 0. Then, in other words, yt is just given by this equation. So now I can just consider the subgroup of G which fix x0. Then this group is one can prove that it's a symmetric product of GA6 with GM. And YT is essentially parameterized by, these are all the cubic fivefold contain X, not a stable one. All cubic fivefold contain the fixed cubic fourfold. Basically, it's parameterized by A28 over G. So now if I want to look at the stable one, so I mean, so I know all of them are half stable, right? Half stable. because the intersection is just x0, which is stable. But now I want to look at the half minus epsilon stable. So my claim is the only unstable one are given by the cone, by G dot cone. Because actually, if you know it's half stable, then you only need to check among all the half, like if you look at the weight, which is 0 with respect to the half linearization, and then among them, you want to say which destabilize your YT. And in other words, essentially, you only need to check. I mean, with a little argument, you can show you only need to check the sigma, which is of the form that lambda 6, lambda 1, and lambda 1, and also the sigma inverse. So if you check this, you find that the only unstable ones are essentially given by the cone and the G dot cone. And then all others are stable. So that's how, I mean, somehow you use this information you get from this, the point half, and then you use some like a wall crossing picture, you understand a lot for the half minus epsilon point. So particularly, if you know this, I mean, basically the GA6 acts on A28 freely. So the quotient will be some isomorphic to A22. And the G acts on this A22 with some weight, like I think a weight like 1.5 on this term. And yeah, I mean, I think 1.5, yeah, basically, depending on the degree, the weight are different. And that's how this like 1 power to 15, 2 power to 6, and this power to 3 come out. So, and so now we know this moduli space. So we constructed this moduli space. The main information we need this moduli space is that outside the codimension 5 closed set, the phi moduli is isomorphic to the cos moduli. So then, in other words, I can just take a big open set. Now I just take the big open set, B0, which parametrize the ones with and the worst one nodal point. And I can shrink this B0 to a little bit, such that it's still big, and it's actually a 5 modular space part. So because we know that this modular stack and the modular space, they only differ by some like codimension, by some like dimension 5 part. So codimension 5 part maybe. Anyway, some like higher codimension part. Let's say. Yeah, I think it's a dimension 5 part. So it's only differed by some like dimension 5 part. And this total dimension 21. So you can certainly have an open set, which is the same as the cos modular space and parameterize all the nodal point. And because it's a 5 modular space, now you can just use the deformation theory to check the Lagrangian fibration structure. So that's, I mean, usually when you check this Lagrangian fiber structure, it's checked on the 5 modular space. But then you prove this 5 modular space is actually just at least on B0. I mean, you already got the 5 modular space. Then that verifies this like a Lagrangian fiber structure. So in other words, we prove this over this B0, this Lagrangian fibration J0, satisfy all the assumptions I need to apply the criterion, the proposition. Then we can just use that criterion to conclude we get a HyperKahler compactification of J bar map to P. So here, again, the point that we make all the computation on B is just to verify that there is a big open set such that the 5 moduli space is isomorphic to the cos moduli space, and this big open set parameterizes the cubic 5-fold with at the worst 1 nodal point. So the second condition is somewhat standard, but the first one, you have to do this calculation. And then at the end of the day, you just have to just prove that this map from this modular space of cubic fourfolds, which is dimension 20, to this modular of this HyperKahler we construct is genetic finite. And because this the the, the HyperKahler we construct is of at least pk number 2. Then if I consider all the Kahler ones, it's at least the codimension 2 in the modular. So now I have some like dimension 20 mapped to something codimension 2, mapping something codimension 2. That means the modular space is at least dimension 22. That will imply the second Belly number is dimension at least 24. So that was what Markman basically already predicted in his strategy. So then we verify that the second Belly number is at least 24. So to get this equality, you need two things. You need that the terminal Q factorial you construct is really I mean pk number 2. So in other words, you actually have to get along the codimension 1 point proper compactification, such that over the codimension 1 point, the fibers are irreducible. And you can always get the fiber to be irreducible, but then you might have a canonical singularity. So basically, you have to construct a explicit proper compactification, such over codimension 1 point, such that the total space is terminal. So that's the first thing. And the second thing that you have to prove that the image basically is the entire like the basically the codimension 2 locus. So in other words, you have to prove that if I deform this Lagrangian fibration to some other HyperKahler still with this Lagrangian fibration, then this Lagrangian fibration also come from some cubic fourfold. So if you prove this image is subjective to this codimension 2 locus, and together with what I just said at the beginning, that you prove the second beta number is precisely 24, and that we didn't treat it in our paper. Thank you very much. Let me stop here.
Okay, so thanks. Any questions, comments? Actually, maybe a very small question. So this reducible symplectic variety that you get, so it's simply connected.
You mean the open simply connect? Actually, let's say I didn't know it could. I mean, especially the open locus, I didn't know it could have a finite fundamental group, but I didn't know. I mean, I think by the decomposition theorem, you can. I mean, some attack cover of this will be simple connected irreducible. Some attack cover of if the open locus has some fundamental group, if you take the attack cover, then that would be a simple connected irreducible one. But I don't know the one I constructed whether it's simple connected, especially the simple the smooth locus. I don't know whether it's simple connected.
Uh-huh.
Sorry, maybe can you say again why the locus where it's a fine moduli space is big?
Yeah, because the stack actually, I mean, this construction we did here is actually completely on the modulus level. So it's actually a stack construction. So then basically we proved the fine modular space which is parameterize the fourfold. The fivefold contain the fixed general fourfold. Is actually just the stack of P one this weighted primitive stack. Now, of course, the singularity of this stack can be easily computed.
Wait, and so there's no issue about stabilizers of the family in codimension 1, for example?
That's right, exactly. We calculated the stabilizer only happened in something like a codimension, like, you know, in dimension 6, something like that, out of dimension 21 stuff. So particularly there is no dimension codimension 1 like an automobile.
Thank you.
Paulo? Sure.
All right, so if that's all the questions, let's thank Chenyang again.
Thank you.
And thank you, Chenyang. And the next meeting is on 27th, yeah?